So I thank the organizers of the IUCAA Summer School and Refresher course for 2020 to give me this opportunity to give an introductory lecture about compact stars. So I will be giving 2 lectures, and I will keep them very basic because the summer school is intended for many undergrad students who are not yet initiated to many of the aspects about compact stars that I will be talking about. What I'm planning to do, though, is to add some of the important derivations in the appendix of the talk, which I will share later on the, I think it's a website which enables the talks to be uploaded. So can you hear me properly?
Yes, go ahead, ma'am.
Okay, thank you so much. So I will also be providing some references to very basic books on pulsar astronomy. So the first lecture will be basically about pulsar astronomy, and the second lecture will be concentrating on how we determine the interior composition starting from the observations that we get from pulsar astronomy. So let's get started. So which compact stars are we talking about? So compact stars, as in white dwarf and neutron stars, these are remnants that are produced at the end point of evolution of stars. I think during this summer school, some of the speakers have talked about evolution of or the life cycle of a star. So in this talk, I will be talking about primarily about neutron stars, but also a little bit about white dwarfs. Both of them are compact stars because they are compact in size. That's the reason. And so white dwarfs typically have masses of about half that of the sun, concentrated within a small radius of only about the radius of the Earth. So you can imagine if you compress the half of the sun into a small radius of that of the Earth, the densities will be extremely high. On the other hand, neutron stars, these are even more dense. So they have masses about 1 to 2 times that of the sun within a small radius of only 10 kilometers. So compact stars are extremely interesting because they are like cosmic laboratories that allow us to study dense matter in the universe. So for light stars like the sun, basically this is what happens. Why do we see the sun as a glowing ball of fire? This is because the star is the sun is actually a gas ball, a gas sphere, which produces thermal pressure by burning hydrogen in the interior, producing helium. And this thermal pressure supports the shape of the star against gravitational collapse. So the sun is typically a light star, but what happens is that from hydrogen, helium is produced. Then helium burning requires higher temperatures. So if this temperature is not available to the sun, this thermal pressure is absent, and now the star starts to collapse. And this collapse leads to an increased temperature, thus igniting the helium and resulting in carbon ignition. So in this way, hydrogen to helium to carbon is produced, and then the star is being light. The evolution halts at this stage, and the end product of the evolution is the white dwarf, basically comprising of carbon and oxygen. On the other hand, for massive stars, like you can see on the right-hand figure, massive stars allow evolution to and producing more and more massive elements in the periodic table. So from hydrogen to helium, then neon, carbon, oxygen, until iron is produced at the center. And if you already have seen this figure from nuclear physics, you might know that it is the binding energy per nucleon which determines whether fusion will occur or fission. So when iron is produced at the center of the massive star, then iron cannot fuse further to produce energy. So at this stage, the thermal pressure support stops, and the star begins to collapse towards the interior. So what happens now is there is a collapse of the outer layers of the star towards the interior. This is a very complex type of physics, and I'm going to simplify this picture for you. So basically, the outer layers start to collapse towards the interior at a certain point when they reach nuclear densities. There is a rebound driving a shock wave. This shock wave expels the outer layers into the interstellar medium, creating a giant explosion, a cataclysmic explosion called a supernova. We also call it a type 2 supernova or a core collapse supernova. What is formed in the center is depends on the initial mass of the progenitor star, and it could be a neutron star or a black hole. So we have to look at a certain important aspect here, and this is called the degeneracy pressure. I'm going to talk about this in more detail in the second lecture, but the basic idea is that in order to balance gravity, there has to be a certain pressure from the constituent particles. For the case of carbon and oxygen white dwarfs, this comes from electrons, because the carbon-oxygen white dwarf comprises mainly of nuclei embedded in a sea of electrons. So these electrons, when the star tries to collapse during the gravitational collapse, the electrons, being fermions, they have a certain kind of property which is described by the Fermi-Dirac statistics. And this is something like social distancing, in fact, because the fermions, they avoid each other. So basically they occupy only one particle per energy level, which leads to an increase in the energy levels until a Fermi energy is reached. So I will be talking about this in the next lecture. And so basically this gives rise to a pressure which is called the degeneracy pressure. Now, in the case of carbon-oxygen white dwarfs, this is enough to support the star against gravitational collapse. But in the case of neutron stars, it is the neutrons, which are also fermions, and the neutrons which provide the degeneracy pressure that now supports the star against gravitational collapse. If the progenitor star is between 8 to 20 solar masses, then it results in a neutron star. But if the progenitor mass is higher than 20 solar masses, then even neutron degeneracy pressure will not be enough to stop it from gravitational collapse, and it forms a black hole. Now, interestingly, this was discovered way back in the 1920s, when first Dirac and Fowler showed that electron degeneracy pressure supports white dwarfs against gravitational collapse. And from this, the maximum possible mass for a non-magnetized white dwarf was calculated by Chandrasekhar in 1931. And it was found that it can support a maximum mass of 1.44 solar masses. This is also called the Chandrasekhar limit. For masses which are higher than this Chandrasekhar limit, both the relativistic, so the electrons become relativistic, and the electron degeneracy pressure will not be enough to support the star from gravitational collapse. And the possibilities were left open by Chandrasekhar. This, however, faced severe criticism by scientists like Eddington. However, it was later proved, and Chandrasekhar was awarded the Nobel Prize in Physics in 1983. So as I already talked about the core collapse, so what is left behind at the end point of this evolution is that there is a compact remnant called the neutron star at the center, and a nebula which comprises the supernova remnant. And if you go to the NASA website, you will see beautiful images of supernova remnants, like the ones you can see in the picture above. Here is an animation of the core collapse supernova. I'm not sure it works on my iPad. Okay, so let's move on. Basically, how do we know that the pulsars that we identify today were rotating neutron stars? So Chandrasekhar already showed that massive stars will collapse. Following this, in 1932, Chadwick discovered the neutron. However, neutrons were already predicted earlier by Majorana, but they were never published. Bade and Sriki introduced the concept of neutron stars, so basically compact stars comprising of neutrons, in 1933. And soon after, Oppenheimer-Volkoff computed what would be the mass of, or the external structure of a neutron star using general relativity, and these are called the Tolman-Oppenheimer-Volkoff equations. So until now, neutron stars were predicted theoretically, but nobody has observed it. Then finally, in 1967, a young PhD student at Cambridge University called Jocelyn Bell discovered pulsating, rotating stars, which she called pulsars. And basically, these were very periodic pulses that were observed at radio frequencies. Soon after, Gold and Pacini proposed the basic lighthouse model for these pulsars in 1968, and it established that pulsars are nothing but rapidly rotating neutron stars. So if we compare the internal structure of a white dwarf and a neutron star, both of them are compact stars, but you can see that for a white dwarf, it's basically carbon-oxygen nuclei with an envelope of helium and hydrogen and embedded in a sea of electrons. On the other hand, a neutron star has a much more complex internal structure. So starting from nuclei at the surface, there is an atmosphere. And of course, after that, there are nuclei, which are iron nuclei at the surface. But as we go towards the interior in a neutron star, the density increases rapidly. And the nuclei become more and more neutron-rich until at a certain point, neutrons start to drip out of the nuclei. And this is called the neutron drip density. So this is the beginning of the inner crust. Following the neutron drip density, the densities in the neutron star are so high that the nuclei start to become deformed. So these are also called pasta nuclei. I mean, this is a fun term, basically to symbolize the various different shapes of nuclei that are formed. So like, it could be meatballs, it could be cheese-like structures, and so on, and until the densities are so high that these deformed nuclei dissolve into a homogeneous liquid. This part is called the outer core of a neutron star. So the outer core is basically made of free neutrons, but there is a small fraction of protons and electrons. In my next talk, I will explain why. And if we go further into the interior of a neutron star, the densities could reach up to 10 times that of saturation nuclear densities that we see generally in nuclear experiments. And there are propositions that there could be strangeness containing exotic components in the neutron star interior. So we will be discussing this in the next talk. So what we know from neutron star observations, from the radio observations, is that there are two kinds of pulsars. So, of course, isolated and binary, but also depending on what is the driving mechanism with which the neutron stars are slowing down, we will classify them as rotation-powered pulsars and accretion-powered pulsars. So the rotation-powered pulsars are the ones where the strong magnetic field of the neutron star, as you can see in the figure, they tear apart heavily charged particles, emitting them in a narrow cone along the magnetic axis, which sweeps the Earth like a lighthouse, which is observed, like Jocelyn Bell observed, as periodic pulses. So in such cases, the pulsars are actually spinning down due to the electromagnetic radiation. And this, here we assume that it is a dipole kind of magnetic field. On the other hand, the accretion-powered pulsars, these are the pulsars which are in binary. And in this case, the pulsar can suck up material from a companion star, which falls, forming an accretion disk onto the pulsar. Such accretion-powered pulsars often emit X-rays. Further, when the accretion stops, the pulsar can spin up because of the accretion of material onto it, which weakens its magnetic field, and these are also called millisecond pulsars. So millisecond pulsars also form a subset of rotation-powered pulsars. Now, these classes of pulsars are nicely summarized in a figure, which is called the P dot diagram. So basically, it's a plot of the spin period on the x-axis and the spin period derivative on the y-axis in log scale. So you can see in the center, the cluster of pulsars, these are the normal pulsars, which are basically the isolated rotation-powered pulsars. We can also see on the left corner of the diagram, the millisecond pulsars. Here, if we assume a dipole formula for the spin down emission luminosity of the pulsar, then we can determine its magnetic field and also its characteristic age. So on this figure, you can see these dashed lines. The dashed lines represent the different magnetic fields and also different characteristic ages. Also, assuming the spin down of a power law, then we can also determine the index, which is called the breaking index of a pulsar. So a breaking index in the case of magnetic dipole radiation would be approximately 3. Now, in this figure, you can also see a class of neutron stars which have very high spin period and period derivative. So basically from the dipole formula, we can determine the magnetic field of these objects, and these are objects with magnetic fields as high as 10 to the 14, 10 to the 15 Gauss. On the other hand, you can see from the figure that normal pulsars have magnetic fields only of about 10 to the 12 Gauss. So these these ultra-magnetized neutron stars are also called magnetars. Recently, there have also been observations of other highly magnetized neutron stars, which are not magnetars, such as X-ray dim isolated neutron stars, rotating radio transients, SXPs, ESPs, and so on. And it is thought that there is actually an evolution between the population of neutron stars and magnetars. Now, in the presence of such strong magnetic fields, neutron stars show features like bursts and quasi-periodic oscillations, basically star quakes. Now, not only radio waves, neutron stars are observed throughout the electromagnetic spectrum. So from the days of Jocelyn Bell, we have moved on, and now we have a multitude of space-based and ground-based facilities which allow us to observe neutron stars throughout the spectrum, from gamma rays to X-rays until radio frequencies. So here is an animation. I don't know if the animation works. If not, you can see at the bottom panel the same Crab nebula, which is being seen at different frequencies. So you can see on the right-hand side, the interstellar dust does not allow us to look into the nebula at visible and infrared and radio frequencies, whereas the X-ray image helps us to look into the interstellar medium, and we can see the pulsar with the beam along its axis. So from using such observations at multiple frequencies, we can actually determine a large number of astrophysical observables concerning neutron stars. So we already spoke about the spin frequency of neutron stars, and these could be as high as 700 Hertz. So it's a rapidly spinning system. We already talked about magnetic fields derived from observations of spins, and also from cyclotron line emission from neutron stars. And the magnetic fields are typically about 10 to the 12 Gauss, but as we already saw, for magnetars, these could be as high as 10 to the 14, 10 to the 15 Gauss. Another very key observable concerning neutron stars is the neutron star mass. It has been observed that neutron stars have masses typically about 1 to 2 solar mass, and the best observations of masses come from neutron stars in binaries. So this we will discuss. Radii of neutron stars are as small as 10 kilometers, and these are determined using thermal and X-ray emission from neutron stars. The mass and radius are the most interesting observables for neutron stars, because the mass-radius relation, which is basically the external structure of the neutron star, can be related to the internal composition of the neutron star using the Tolman-Oppenheimer-Volkoff equations, which are hydrostatic equilibrium equations. So it has been seen that the imprint of the neutron star interior composition is seen very clearly on the mass and radius. However, the radius determinations from the thermal and X-ray emissions from the surface emissions from neutron stars have very high incertitude. So astronomers use a number of complementary astrophysical observables concerning neutron stars. For example, the moment of inertia for rotating neutron stars. The moment of inertia from classical mechanics is, we know that it is proportional to the product of the mass and the square of the radius, which means that if one of the the mass or radius is known and the moment of inertia is known, then we can determine the other. On the other hand, gravitational redshift from spectral lines can also constrain the ratio of the mass to the radius of neutron stars, also known as the compactness. And the surface, the thermal emissions from neutron star also help us to Can you see me? Can you see my screen?
No, ma'am.
Okay. Can you see the screen now?
Yes.
Okay, thank you so much. All right, so neutron stars. So we were talking about the different astrophysical observables that can be determined from observations of neutron star across the electromagnetic spectrum. Neutron stars can be seen also in an X-ray spectra. So the Chandra telescope has recently given us a lot of important information about neutron stars in the X-ray band, X-ray frequencies. So direct surface emission, so thermal emission from the neutron star surface is seen in X-rays. And you can see at the bottom a figure that shows the temperature, the surface temperature of neutron star versus its age. And so if the age and the heating mechanism is known, one can determine the cooling rate of neutron stars. If the atmosphere, the composition of the atmosphere is very uncertain even now for neutron stars, but if the atmosphere and the distance to the neutron star is known, then from the surface thermal emission, one can determine its radius. Further, like I already said, from spectral lines in X-rays, one can determine the redshift. So basically the redshift is the fractional difference between the wavelength seen by the observer and the emitted wavelength. And this redshift depends on the compactness of the star, because the redshift depends on the space-time, and the compactness of the star tells you about the surface gravity of the star. So the redshift gives us information about the ratio of the mass to the radius. Recently, in 2017, there was the launch of a mission called the NICER mission, the Neutron Star Interior Composition Explorer. And the aim of this mission is to determine very accurately the radii up to even 5% of accuracy. So the idea of this is that the NICER mission models the general relativistic effects on the pulse profiles of rotating hotspots seen in X-rays from millisecond pulsars. And these, again, depend on the compactness or the mass to radius ratio. Neutron stars can also be seen in gamma rays. So the Fermi LET, or the Large Area Telescope satellite, has detected more than 150 gamma ray pulsars. Gamma rays also give us information about several astrophysical phenomena associated with neutron stars, particularly gamma ray bursts. So gamma ray bursts are I don't want to talk about gamma ray bursts in this lecture because these are quite complicated astrophysical phenomena. But just to give you an idea, there are two classes of gamma ray bursts, so long and short. And the long gamma ray bursts are associated with the collapse of stars, like the supernova explosion. Some of them have a supernova association, whereas the short gamma ray bursts are associated with mergers of neutron stars. So again, gamma ray sky gives us information about neutron stars. Coming to neutron star masses, neutron star masses can be accurately determined, particularly in the case of neutron stars in binary, from pulsar timing. So the orbital analysis gives us information about the neutron star mass. So in addition to the normal Keplerian parameters, one can also observe post-Keplerian general relativistic parameters, and these in turn depend on the total mass and the mass ratio of neutron stars. So relativistic advance of periastron, gravitational redshift and time dilation, orbital decay in the period, and Shapiro time delay. These are some of the post-Keplerian parameters which are related to the total mass and the mass ratio of the neutron stars in the binary. And from these, one can determine the individual masses in the binary. For the case of X-ray binaries, so pulsars in X-ray binaries, the determination of mass is possible due to events like eclipses and so on, but this is much more complicated because of accretion processes and so on. So here is a list of the different neutron stars which have been determined. So from the mass distribution of neutron stars, you can see that most of the masses have been concentrated around a canonical value of about 1.4, whereas the lower tail, you can see that there are several high mass neutron stars which have been observed recently. So these very high mass neutron stars are actually particularly interesting for constraining the interior composition. And this is because, like I already told you, the core composition determines the equation of state. Equation of state is basically the relation between the pressure and the density of the neutron star. And depending on the core composition, the equation of state will be different. And the equation of state can be mapped to the mass radius relation of neutron stars. So determination of the mass and radius of a neutron star in turn allows us to constrain its equation of state and therefore determine what is the core composition of the neutron star. So the maximum mass of the neutron star should be able to be explained by the theoretical prediction for the equation of state. Recently, there has been a totally new window which has opened up with the detection of neutron stars in gravitational waves. So gravitational waves had been indirectly measured by Halsey and Taylor back in 1974 when they observed the pulsar system, a binary pulsar system, which was losing energy by emission of gravitational waves and therefore approaching each other. And this led to a cumulative shift in the periostron time. And this prediction matched exactly the general relativistic prediction. And this was the first indirect observation of existence of gravitational waves and emission of gravitational waves from neutron stars. And therefore, Halsey and Taylor were awarded the Nobel Prize for this discovery. And motivated by this discovery, and with the rapid technological advances, several gravitational wave detectors were built across the globe. As you can see, the LIGO detector and the Virgo detector at the bottom. The LIGO detector at the Hanford and Livingston sites in the US, and Virgo at the Italian-French border. And the idea is to capture gravitational waves emitted by neutron stars. So gravitational waves can be emitted by both isolated and binary neutron stars. And what is the most interesting is that these gravitational waves carry information about the interior composition of neutron stars. So not only that, the electromagnetic observables that we talked about earlier, these were indirectly probing the neutron star, and there is always modeling involved. But here, gravitational waves bring us information directly from the interior of neutron stars. So particularly interesting is the case of binary neutron stars, because as you can see in the animation here, when neutron stars merge in a binary, they deform each other tidally, like the moon and the sun and the tidal effects that we see on Earth. So these tidal deformability, lambda, is actually related to the in the equation you can see above, it's related to C, which is the compactness parameter. So basically, compactness, which is the mass to radius ratio, now gives us again information about the interior composition of neutron stars. So on the right-hand figure, you can see that these were the initial estimates of the tidal deformability and its effect and the effect of compactness on these parameters, which were deduced from the first observed binary neutron-star merger. On the other hand, there are also gravitational waves emitted from isolated neutron stars that we still have not observed. And what we need is a time-varying quadrupole. So rotating, deformed, or oscillating neutron star will produce such a time-varying quadrupole, which will emit gravitational waves. So neutron stars can be deformed in various different ways. So in the picture on the top left, you can see so the spinning down of a neutron star. So basically the frequency and versus time. And usually neutron stars, as we already saw, they are rotating extremely periodically. And however, there are cases when there are sudden glitches or jumps in the neutron star spin period. And these glitches actually are sudden spin-ups due to rearrangement in the neutron star interior. And these could also emit bursts of gravitational waves. There could also be flares and outbursts from strongly magnetized neutron stars or magnetars, which would also be sources of gravitational waves. Further, very strong magnetic fields also deform the shape of the neutron star into an elongated shape, and such a rotating elongated neutron star will also emit gravitational waves. There could also be a small deformation or bumps on the surface of a neutron star. These are called mountains. Mountains because even a mountain on Earth would be crushed to a few centimeters on the surface of a neutron star. So such mountains can also be sources of continuous gravitational waves. What are even more interesting is that just like earthquakes, there are star quakes in neutron stars, and these have different modes of oscillation. Depending on the restoring force which brings the system back to equilibrium, these have been classified into fundamental F modes, pressure P modes, gravitational G modes, rotational R modes. So these four modes are basically fluid oscillation modes, which are also seen in stars. But in addition, neutron stars are highly relativistic, so there are also space-time or W modes. So not only isolated neutron stars have these oscillation modes, what is interesting is that there could be imprints of these oscillations even in the inspiral, the merger, and the ring down phases of neutron stars, which can give us further information about the interior composition of neutron stars, because these modes again depend on the composition. So just to give you an example, for the case of the rotational R modes, it was shown that R modes are present in all rotating neutron stars. So all rotating neutron stars are basically unstable with respect to rotation. And so once these rapidly rotating neutron stars are unstable to R modes, they emit gravitational radiation. The only way that the star can counterbalance this gravitational wave emission is by leptonic weak processes in the neutron star, and which produces bulk viscosity to balance out the gravitational wave emission. And these leptonic processes are basically involving the different components of neutron stars. So if only neutrons, protons, and electrons are present in neutron stars, then these would produce the black curve that you see in the figure. So basically this figure, which shows the critical angular velocity versus temperature, this is called the instability window of R modes. And so this is defined by the balancing of the bulk viscosity and the gravitational wave emission. So you can see that on the high temperature side, it is these URCA processes, or the weak processes involving neutrons, protons, which balance out the gravitational wave emission, whereas at the low temperature side, the window is defined by shear viscosity, again coming from electron-electron collisions. But again, if there are some other components of such as hyperons, so these would produce additional weak processes in neutron stars, and these would also change the window of where these two forces balance each other. So if there is a rapidly rotating neutron star, which is cooling down, it enters at a certain point the instability window, then it becomes unstable with respect to R modes, starts to emit gravitational wave, slows down until it reaches the other edge of the instability window. And here, the neutron star starts to rotate stably, which means that we have here two kinds of signatures, one coming from gravitational wave and the other coming from the observation of spin periods of neutron stars. So basically, these two combined will give us information about neutron star interior composition. Now, what was spectacular is that in 2017, there was the first evidence, the first observation, the direct observation of gravitational waves from a binary neutron star merger. This event is called GW170817. And what was spectacular about this observation is that not only was it observed in gravitational waves, but simultaneously there were electromagnetic counterparts which were observed. So basically, this merger, it was associated with a kilonova event in the optical. It was a gamma ray burst was detected in the gamma ray frequencies. Further infrared emission, ultraviolet emission, X-rays, and even radio emission was detected for this event. And in one event, it confirmed a lot of different theories related with neutron stars, such as a kilonova and short gamma ray burst binary neutron star merger association. This picture summarizes what I just said. So basically, so Fermi and Integral observed the gamma ray components of this event. VLA detected the radio counterpart. The X-shooter on VLT also observed the kilonova event, and the Chandra also observed the X-rays. So this event marked what is called the beginning of the multi-messenger astronomy era, because neutron stars are observed throughout the electromagnetic spectrum and now also in the gravitational wave frequencies. So combined can help us verify the different astrophysical models of neutron stars and help us understand the different processes associated with such events. There are also updates about the upcoming third generation gravitational wave detectors. Kagra has already started operation in Japan. LIGO and Virgo are upgrading. So the advanced LIGO and advanced Virgo, so the LIGO-Virgo collaboration currently due to the coronavirus crisis has stopped operation, but soon we will also have the LIGO India joining the consortium of gravitational wave observatories. And in addition, there are plans to extend the multi-wavelength astronomy across the electromagnetic band. Theseus, CTA, there are projects, so in gamma rays, for X-rays, the NICER mission has been launched. There are upcoming missions like Athena, Lynx, SVOM. In the optical band, the TMT is coming up, the 30-meter telescope. AstroSat is a multi-wavelength telescope which observes neutron stars across different frequencies. And radio, there is the SKA, which is coming up. So basically, in addition to gravitational wave emission, we will now have information coming about neutron stars throughout the electromagnetic spectrum, which is going to enrich our information, enrich our understanding of neutron stars. So here are some references for further reading. So Weber, Shapiro-Tucholsky, and further there are, I will provide you some other references which will later, which will concern the equation of state problem of neutron stars. So basically in the next lecture, I will be talking about how to model the interior composition, which is extremely challenging because it involves multidisciplinary studies like particle physics, condensed matter physics, nuclear physics, general relativity, and so on, and how to combine these information with the astrophysical observables we talked about today and nuclear and heavy ion experiments. So thank you very much for your attention, and if you want, you can also contact me by email, social media, and I will also upload some of the lectures on my website, on the online resources. And I'm also going to add the mathematical derivations of what I talked about today in the appendix of the PDF lectures that will be available to you. So thank you very much, and looking forward to the questions.
Hi there, Udri. Can you hear me?
Yes.
So now we have 5-6 questions. So at first, I will unmute Vaishnavi. So please ask your question.
I cannot hear.
Vaishnavi?
I cannot hear you. Yeah.
So I am asking to unmute.
Probably a network issue.
Most probably.
Or
am I audible?
Yes, yes.
Ma'am, my question is with respect to pulsars. So what would be the position of rotation-powered pulsars and accretion-powered pulsars in the instability strip in the HR diagram? Would they be placed closely or far away?
So I'm not sure I understood the question.
Ma'am, should I repeat?
So you were asking about what would be the position of rotation-powered pulsars and accretion-powered pulsars in?
The instability strip in the HR diagram.
So actually the HR diagram, what it signifies is, well, I'm not sure about this answer because I'm not sure about this answer, sorry.
Okay, so we'll move to the next question by Junique. So I am unmuting you.
Hello, ma'am. Good afternoon. Am I audible?
Yes.
Thank you, ma'am. Ma'am, my question is that those neutron stars, are they responsible for fast radio bursts, FRBs?
Actually, well, it's a good question, but FRBs are actually, I mean, it's still not clear what is the process because it is thought it could be associated with neutron stars, but also there are some other alternative theories. So it's not yet clear whether FRBs are associated with neutron stars itself.
Can you please tell what are the possibilities which majorly indicate that they can be from neutron stars like that?
I think in the case of neutron stars, it is thought that basically magnetars, so magnetar flare releases electrons and charged particles, and so basically this could collide with the remnants, and so basically these electrons can generate radio waves, and the shock, while it slows down the radio signal, can be observed as fast radio bursts. So if I understood correctly, so this is one of the interpretations, but there are also other interpretations. So this is the one which I am familiar with, but I mean, there are also other interpretations, and I think the question is still open.
Thank you, ma'am.
Okay, then we'll move to the next question by Akash Chaudhary. Akash, you are unmuted. Please ask your question.
Hello, good afternoon, ma'am.
Hello.
Ma'am, my question is like the jets from the pulsars, they have specific direction. Like, what's the reason for the particular direction of the jets from the pulsar?
So you mean the electromagnetic emission, right?
Yeah, ma'am.
I mean, basically, it's the strong magnetic field of the pulsar. What it does, it strips the charged particles and then emits them along the magnetic axis. So basically, it acts like a generator, which strips the particles, and these are accelerated along the magnetic poles. So this is why you see this emission along the magnetic axis.
Okay, thank you.
Okay, is there any other time to take any more
Yeah,
further
I think
questions?
maybe one or two short questions.
Okay, so
or should I go to the, maybe I will go to the YouTube questions?
I think so, because I cannot find.
Okay, thank you, Bhaskar. So there was one question from Aniket Ganguly. How is the shock wave generated during the core collapse? So yeah, I skipped a lot of very interesting physics of core collapse supernovae. So the shock wave, how the shock wave is generated, this is actually an open question, because there is a lot of astrophysical modeling that goes into it. Basically, there is this infalling material from the outer layers, which through photo disintegration of nuclei generates electrons. These electrons start to capture protons and producing neutrons. So there is neutronization, producing neutrinos. So these neutrinos carry energy. So when these neutrinos leave the star, they carry away energy. And what happens is that when the outer layers, they reach the core of the collapse, which is at nuclear densities, there is a rebound, and it is thought that the electrons, the neutrinos could revive the shock and expel it towards the exterior. But this has actually a very complicated question, and there have been a lot of different components of physics which were missing, and currently these are being looked at again in order to generate the sizable shock that is actually seen in astrophysical supernovae. There is a question from Ayush Sahu. How is degeneracy pressure overcome? Would that not violate Fermi-Dirac statistics? how is degeneracy pressure overcome? Do you mean that in the case of, I don't know what you mean, but I am assuming that you mean that for the case of white dwarfs, for example, it is the electron degeneracy pressure which balances the gravitational collapse of the white dwarf. For the case of neutron stars, the mass is much higher, so the gravitational collapse in this case cannot be halted by only electron degeneracy pressure. So once the mass exceeds the Chandrasekhar limit, then the collapse continues because it cannot be supported by the electron degeneracy pressure. So it does not violate Fermi-Dirac statistics, because basically the collapse and basically it is the balance of these two forces, so the pressure and the gravitational force which balance each other in so that it could be a stable system. Agam Jha asks a question: can gravitational waves be taken as the signature of deconfined state at the interior of a neutron star? So there are many signatures of deconfinement in the interior of a neutron star. So deconfinement is associated with a phase transition, and a phase transition from hadrons to quarks would manifest itself also in electromagnetic radiation. And for gravitational waves, yes, like I said, that the different mode oscillations, the different the tidal deformability also. It was actually, I worked on this problem and I showed that the tidal deformability depends on the equation of state, depends on the interior composition, and if there is a strong phase transition, it can actually violate a relation called the I love Q relation, or the relation between moment of inertia, the tidal deformation, and the quadrupole moment. And yes, it would definitely show up in the signature of the gravitational waves. Also, for the isolated oscillation modes, there are signatures of the equation of state of the quark phase transition in the gravitational wave. There is another question again from Akanksha. I think this would be my last question. So what is the temperature at the interior of a neutron star? So actually, when neutron stars are born, they are called proto-neutron stars. So these newly formed neutron stars, which are the remnants of supernova explosions, these are particularly hot. So they are about 50 MeV in temperature. But gradually, neutrinos take away energy from the system, and they start to cool down. So within a very short time, they cool down. And the temperature drops to about a few MeVs. And this is actually very low temperature compared to the excitation energies of the particles. So in effect, we consider neutron stars to be zero temperature systems. So I think that if there are no other questions, is there any other question on Zoom? Or otherwise, I think...
we have a hand raised by Shatnik Bhattacharya. So,
okay,
I'm unmuting him.
Good afternoon, ma'am.
Hi.
Ma'am, is it possible to study properties of accreting neutron stars by performing precise astroseismology of their companion?
Companion in the sense, astroseismology exists also for normal stars and for compact stars, right? So we are talking about accreting systems, and accretion of from the companion star can occur in neutron stars from the companion star could be anything. It could be a white dwarf, it could be okay, for example, if it's if it's an accreting system, it would say be a normal star. So if you mean that whether there will be imprints, I don't know if you mean whether there will be imprints of the I mean, astroseismology basically means to find imprints of the interior composition of the star on the oscillation modes or on the gravitational waves, so on the oscillation modes. So, I mean, irrespective of whether it's in a binary system or in an isolated system, there are the oscillation modes will carry signatures of the interior composition of the neutron star.
Man, my actual question was, does the accreting neutron star leave imprints on the internal structure of the companion, which might reflect on the astroseismology of that companion star?
Well, if the companion star is a main sequence star, I mean, I would say, I mean, this is a more relevant question when you're talking about binary neutron star system. There, of course, yeah, because this would be an interesting question in that case, because both of them are neutron stars and there is tidal coupling as well as imprints of the internal composition. But when it is not a neutron star, the companion is not a neutron star, in that case, I mean, it is there will be interaction between the two, but the imprint on gravitational waves would be very difficult to find. I don't think you can. Does that answer your question?
Okay, ma'am. Thank you.
Okay, so maybe the last question, a very general question by Madhusudan. He asked why people believe there could be some strange matter inside a neutron star.
Okay, actually in my next lecture, I will be talking about this in detail. So the thing is, strangeness has been seen in terrestrial experiments, in like heavy ion collision experiments, like these particle accelerator experiments like LHC at CERN and GSI and so on. And in those cases, what has been seen is that there are strangeness containing particles like hyperons, kaons, which appear only momentarily. But in case of neutron stars, the high density environment actually provides a possibility for these to be the strangeness containing components to be stable properties of stable components of the interior. And this is because the high density allows the particles, so the neutrons and protons to be, neutrons and electrons to be energetic enough so that, and massive enough so that they may form these heavy baryons or heavy mesons. So I will actually show this in much more detail in my next talk, which is tomorrow at the same time. So if there are no other questions, then I think I will thank you all for your attention, and hopefully you will attend my lecture tomorrow. If you have any further questions, don't hesitate to email me.